All this is on the camera then. Well, Tony, I didn't memorize your title, but we can all read it. Prudent and quasi-prudent self-avoiding walks and polygons. And of course, we're anxious to hear what's prudent in this context.
Thank you very much, and I too would like to thank the organisers. I know everybody has thanked the organisers, so it might feel formulaic, but it's no less heartfelt for that. This has been a wonderful meeting, and I'm sure everybody has enjoyed it very much. This is a talk that I've given some aspects of before, but it's an ongoing calculation. I'm not sure how far I'll get. Hopefully I'll only get about halfway through, so then I can do the other half in Vienna. So you're all, I hope, will be in Vienna to hear the second half of the talk. The talk, this problem stems from my long-standing interest in self-avoiding walks, a problem which goes back now probably more than 60 years, and it is...
Your interest?
The problem, Alan, the problem. And it is in fact quite extraordinary how few really significant advances have been made in the last 40 or 50 years. Somewhere between 40 and 50 years ago, there were some very significant results obtained principally by John Hammersley and Harry Keston, and there have been comparatively minor improvements since then, but in terms of rigorous results, at least for 2 and 3 dimensions, of course there's some very beautiful results in higher dimension by Slade and Hara and others, we still know remarkably little. So just to set the notation, and I'll leave this transparency here, for self-avoiding walks we denote by C subscript n the number of n-step self-avoiding walks equivalent up to a translation, and it is believed that asymptotically for large n the number, this is for self-avoiding walks on a regular lattice, think of Z2 or Z3, grow like a constant times mu to the n to the gamma minus 1. From the work of Hammersley we know the exponential growth, so very crudely speaking we know this mu to the n is known, n to the gamma minus 1 is not known rigorously in dimensions 2 or 3, though it is known that this is the subdominant term in dimensions 4 and higher. In fact, it's quite remarkable that we can't even prove the existence of this exponent for 2-dimensional self-avoiding walks. The other quantity of interest is the metric property, in this case the mean square n to n distance, or equivalently the radius of gyration, or the mean distance of a monomer from the origin, which also grows algebraically like in this manner, n to the 2 nu, and again the existence of this exponent nu has not been proved in dimension 2 and 3. Of course, for random walks we know what this is.
Amazingly, I don't think it's ever been proven that nu is greater than or equal to a half, or even that nu is greater than or equal to 0.2.
Well, if you can't prove it exists, it's very difficult to prove its value.
No, but you could define it. You could define it in a lim-inf sense. I don't know whether there's any lower bound on the growth of the end-to-end distance.
The value of mu, the growth constant, is of course lattice dependent, and in fact the only exact result, and I'm talking in the Baxter sense here, where Rodney Baxter distinguishes exact results from rigorous results. Exact results are those that every reasonable man or woman knows to be true, and of course I don't have to tell you what rigorous results are. So this is an exact but not rigorous result due to our chairman. More than 20 years ago, Bernard found this wonderful result for the growth constant mu on the honeycomb lattice, and we don't have any other results, though we have some excellent numerical results. This is the best numerical estimate we have for mu on the square lattice, and there is a conjectured quadratic equation in mu squared. You can see this is an algebraic number, satisfies a quadratic equation in mu squared. you can play some numerical games and find a quadratic equation in mu squared which has this numerical value as a root.
Do you think it's
as
true?
many digits?
Sorry?
In as many
Yes.
digits? So why did you show it? There is a blackboard.
Unfortunately, well, I can't remember the digits, but it's one of the digits is 529, the other is 11, and the other is 7.
Okay.
So the chances of it being true, all right, that's another.
The inverse of those numbers.
Very briefly, when you obtain that result, I had this to 6 digits, and I started looking for algebraic equations, and the best one was the one I'm speaking about. And then as we got longer and longer series, we got more and more digits, and it keeps fitting. So it has, as time has evolved, that particular equation has fitted for 6 digits, 7, 8, 9, 10, 11. So, but I'm not even prepared to make a conjecture. I had our other organizer of this conference, Alan Sokal, once quite wisely said, when people quote numerical results with some sort of errors or conjectures, the person making the result should assign an amount of money to it. So, here's an error bound at the $10,000 level. That means that you are prepared to bet $10,000 or whatever of your money on that. So I'm not prepared to bet more than $1 on that particular polynomial.
Australian dollar?
Australian dollar or American dollar?
Even a euro. And this is another result that that followed from Bernard's calculation of the honeycomb lattice, that gamma is 43 over 32 and that nu is equal to 3/4. In 3 dimensions, we have only numerical estimates, and indeed there is no reason to believe that the critical exponents should even be rational in 3 dimensions. A subset of self-avoiding walks is that of self-avoiding polygons. A self-avoiding polygon you can consider as a self-avoiding walk that finishes one step away from its origin. And if we denote by p sub n the number of n-step self-avoiding polygons equivalent up to a translation, they grow like mu to the 2n. Because I'm talking about polygons now on so-called loose-packed lattices, such as the square lattice or the simple cubic lattice, where polygons must have an even number of steps. So of course Pn, where n is odd, is 0. So this only applies to the number where n is even. Grows like mu to the 2n, n to the alpha minus 3. And we have a similar measure of the spatial dimension. One measure is the caliper span, dn. Another is the radius of gyration. So this is the same exponent nu that appears for self-avoiding walks. Alpha is a half in 2 dimensions. Again, an exact but not rigorous result. And result that Hammersley proved, which is by no means obvious, is that mu for self-avoiding polygons is equal to mu for self-avoiding walks.
Should this also be mu to the n?
Where?
Because that's a little bit confusing. The number
Yeah, it
of
should be mu to the end.
self-avoiding walks should be bigger than the number of polygons.
You-
I think you were.
Sorry, this should be 2n.
Yeah, okay, then that's
May I make a comment? Tony?
Yep.
May I make a comment? See,
Yes.
conformal invariance has not been represented much in this conference, so maybe maybe most of people know about it, but in a way, the situation for this problem is a bit like in a pyramid. So you have the real chamber in the pyramid. You know it's there, you know there is a treasure, but you don't know exactly which paths to take to reach that treasure chamber which has not been explored yet. So, but in a way, so in 2 dimensions at least, people know very well what the continuum limit of this open block is, which is the SLE itself. Of course, the point is to prove rigorously that the the limit of self-avoiding walk is SUV itself.
Yep.
Provided if you know it's constantly invariant, then that would be enough to SUV itself. But once you know that, you have really a tool which, a mathematical tool which allows you to predict enormous, to calculate to derive an enormous number of properties. So you're right in terms of rigor, but still, as you know, behind the walls there is this enormous
Absolutely.
Body of knowledge.
And indeed, there are, well,
This is almost within reach.
This touches on that. One property that's of interest with self-avoiding polygons is not just the number with a given perimeter, but if you think of these on the square lattice with unit spacing, you can consider the area that is enclosed by the polygon. You can associate fugacities with area and perimeter and get models of vesicles, which was first done by Fisher. And indeed, you can look at the two variable generating function for this in terms of area and perimeter. And I'll say more about that in just a moment. So because in terms of rigor, it's so difficult to solve these models, there's quite an industry, particularly in the combinatorics community, looking at simpler models. So we seek easier, preferably solvable models as close as possible to self-avoiding walks, and in particular we want to retain some of the important properties of self-avoiding walks. There's no point simplifying the model so that it becomes uninteresting. So what constitutes an interesting model, as Alain Lascaux likes to say? So one of the properties we would like is for whatever model we propose should have a growth constant as close as possible to that of self-avoiding walks. If we look at a subset of self-avoiding walks, generally speaking, that subset will be exponentially rare among self-avoiding walks, so mu for the model will be strictly less, but the closer this is, the closer we get to the model. Nu being 3/4 is a property of self-avoiding walks, a very specific property, so we would like that, and that's probably a more fundamental exponent, and gamma as close to 43/32 as possible. So an obvious trivial model is to take a directed walk, where you say, for example, that you can only take steps in the positive x direction. You can never take a step in the negative x direction, but then you can go plus minus y. And then it's utterly trivial to solve this model. You find that mu is 1 plus √2, nu is 1, gamma is 1. So you can see, if you recall, mu here is 2.6 something, whereas here mu is 2.4. A model of staircase polygons, a more primitive model, where you just take two directed walks with a common origin and endpoint. The generating function is, or the number of these is given by the Catalan numbers. This is the generating function, from which follows that Pn goes like a constant 4 to the n to the minus 3/2 for n even, and so alpha is 3/2. The fact that alpha is 3/2 for staircase polygons and alpha is 1/2 for self-avoiding polygons is kind of suggestive. It means that if you look instead of at self-avoiding polygons at rooted self-avoiding polygons, you pick up another factor of n, and so for rooted self-avoiding polygons this increases to 3/2, and in fact it turns out, again this is conjectural and not rigorous, that if you look at the two variable generating function at the tricritical point for staircase polygons and for rooted polygons, it turns out that the scaling functions are given by the Airy function, which suggests an underlying Brownian excursion, and this connects these two models, the self-avoiding polygon and the staircase polygon, at the tricritical point. But that's the subject of another seminar, but it's an interesting observation and brings us closer to SLE. Looking at simpler models is really the subject of my talk today, and I'm going to look at a simpler model called a prudent self-avoiding walk, and if time permits, I'll also discuss quasi-prudent, which is a relaxation of the prudent model. The people involved in this are listed there. John Dethridge is a lamented ex-PhD student of mine. He was a brilliant student, did some very nice work, and around the time he started to write up his thesis, he was courted by Google and ran off to America, never to be seen again or heard from again, but is no doubt making large sums of money working for Google, never completed his PhD, never responded to any of my emails, but was responsible for much of the work that underlies this. Tim Garoni has recently joined me after a spell with Alan in New York, and he's responsible for some of the work I'm going to talk about in quasi-prudent self-avoiding walks if I get there, and Ivan Jensen is a long-term collaborator of mine at the University of Melbourne. Okay, a prudent self-avoiding walk is a proper subset of self-avoiding walks on the square lattice. The walk starts at the origin, and the empty walk is a prudent self-avoiding walk. A prudent walk grows by adding a step to the endpoint of a prudent walk such that the extension of the step by any distance never intersects the walk. What this means, if I can find it. So if you have a go along here, that is forbidden because the extension of this will see the walk. So the idea is that you are so careful that you will never violate the self-avoiding walk constraint that if you can see another vertex in the direction you're travelling, no matter how far away, I won't go there. So that's prudent. Hence the name prudent. The walk is so careful to be self-avoiding that it refuses to take a single step in any direction where it can see, no matter how far away an occupied vertex. Is that prudent enough for you? So let's grow one. So you see it can't turn left now, it has to go straight ahead or right. So that's okay, so there's a prudent self-avoiding walk. And there's a slightly larger one. The origin is marked in green. Unlike ordinary self-avoiding walks, prudent self-avoiding walks will not generally be reversible. That is, this is obviously a prudent walk, but it's obviously not if you start going in the opposite direction. The model...
But you're not thinking about it as a growth process.
No.
You'll enumerate all n-step self-avoiding
with equal probability.
Self-avoiding walks with equal probability.
Correct. The model was introduced in an unpublished manuscript by Pascal Preyer in France and further developed at the 2005 FPSAC conference by Enrica Ducci. There is a growth process, which is what Alan just referred to, which are called outwardly directed self-avoiding walks by Santra, Seitz and Klein in the physics literature, also by Turbin, but as Alan has insinuated, they view it as a growth process where not all walks are weighted with equal probability, rather you weight each walk by the product of the probabilities of the individual steps. Some further very recent developments have been obtained by Mireille Bousquet-Melou. These will be reported at FPSAC this year, and I'll allude to one of them shortly. For which model? For the prudent self-avoiding walk. Yep. So, as I just mentioned, unlike self-avoiding walks, prudent walks are usually not reversible. Unremarkably, each prudent self-avoiding walk possesses a minimum bounding rectangle, which is obvious. Any walk possesses a minimum bounding rectangle. But what is less obvious is that the endpoint of a prudent walk is always a point on the minimum bounding rectangle. So when you take a step, you're either lying on the boundary of the existing minimum bounding rectangle, or you are extending the minimum bounding rectangle. We follow Ducci and consider three variants of prudent self-avoiding walks. The first is called type 1 and forbids step sequences to the west, followed by steps to the south, and also south followed by west. That is to say, you're not allowed to go west-south or south-west. So the consequence of this is that type 1 prudent self-avoiding walks will only end at either the top or the right-hand edge of their minimum bounding rectangle. You can see if you had, if these steps were allowed, you could end up here on the leftmost edge or indeed on the bottommost edge. So these are walks that must end along here or along here. And we denote the generating function in the usual way with a superscript 1 to indicate that I'm referring to type 1 prudent walks. Cm, same notation as I have here, the number of m-step type 1 prudent self-avoiding walks. And here is an extremely crude sketch of what one of these things look like. A typical type 1 prudent self-avoiding walk is just a series of these directed walks going east essentially, then north, then east, then north. So this is what we've got here. So that's a typical type 1 prudent self-avoiding walk. To calculate the generating function, Ducci considered 4 different subclasses. She broke them up into 4 different subclasses, obtained a system of algebraic equations, which she was able to solve by the kernel method, and found this result. Nice algebraic expression, and you can see that the nature of the singularity will either, depending on where the zeros of this lie compared to the zeros of this, you'll either have a simple pole singularity or a square root singularity. Well, when you do the numerics, it turns out that the zeros of this polynomial are closer to the origin than the zeros of this singularity. So this gives you the dominant behavior, so that Cn1 behaves like a constant times mu1 to the n, 1 plus big O 1 over n, where 1 over mu1 is the smallest positive root of this polynomial. And you can see you'll get a second singularity coming from the square root here. The smallest root is at 0.40303, but note a second singularity at the zeros of this polynomial, which gives you a second singularity at root 2 minus 1, or 0.414213, which from a numerical point of view does raise some difficulties if you're trying to find this and just from the numbers. But of course you're not, because we have the exact solution. So more precisely, if we want to include that subdominant term, there's the coefficient of x to the n in the generating function is a constant times xc to the minus n, 1 plus terms of order 1 over n, plus a second constant times x star, which is the root 2 minus 1 to the minus n, n to the minus 1/2. The generating function is algebraic of degree 2, and you can convert this, if you prefer ODE representations, to a second order ODE, of course, with polynomial coefficients. So the growth constant is the reciprocal of xc, which is 2.4811, which can be compared to this result for the self-avoiding walks and this result for directed walks. So this is a more interesting model in that than directed walks, because mu saw minus mu model is now closer, is smaller than in the case of the directed walk. So we're getting closer to self-avoiding walks. So this is a less rare subset of self-avoiding walks than directed walks. And as I just showed you on this sketch, generically a type 1 prudent walk looks like a series of directed walks glued together in 2 orientations. So its algebraicity is perhaps not too surprising. nor is the presence of the subdominant singularity, which is the singularity of the directed walks that make up the prudent walk.
All this is on the square lattice.
Yes. I'll have something to say about the cubic lattice. The unsolvability of the self-avoiding walk model means that, well, this is just the salesmanship trying to justify why I'm even bothering. And the fact that the growth constant is closer to the growth constant for self-avoiding walks than I put most there, because until I discuss quasi-prudent walks, I could have put actually any. I don't know any other model that gets closer to mu. And while the algebraic nature of the solution makes it of limited pedagogical value, because we certainly know that for true self-avoiding walks they're not algebraic, the generating function, we'll see that it's not the case for less restricted versions of prudent self-avoiding walks, which I'll look at right now. Unfortunately, it seems that we can't escape from nu equals 1, where nu is the exponent here. And that's hardly surprising that nu should be 1, because we've really just got a sequence of directed walks for which nu is equal to 1. The second type of prudent walk, which gets closer to the full definition, which is imaginatively called type 2, forbids sequences west followed by south when the walk is at the top of its minimum bounding rectangle. So here's the minimum bounding rectangle. You can't go like that, and forbids west followed by north at the bottom. So that means that the walk will not finish on the left-hand edge, or to put it another way, the walk will finish on one of these 3 sides. See, type 1 finished on 2 sides, type 2 finishes on any of 3 sides, and the full prudent self-avoiding walk, of course, has a symmetry which allows it to finish anywhere. And you can even consider directed walks as type 0, because they really can only finish on one side effectively. As I just said, such walks can end at the top, the right-hand side, or the bottom of their minimum bounding rectangle. We similarly denote the generating function as C2x, where the superscript 2 refers to type 2. Cm is the number of such type 2 walks. And it was the solution of this that was reported at FPSAC in 2005. Ducci treated it by breaking it up into 10 different cases and got 10 functional equations and solved them by the kernel method, giving an algebraic generating function of degree 4, which unfortunately is wrong, due to a subtle cancellation, which means that at one point one has 0 over 0. It was subtly wrong. When I started studying this problem,
That is, she didn't notice.
She didn't notice. We noticed when I started I took her results and expanded it and looked at the series, and at the same time generated the series for the full problem, and found that for n sufficiently large, the number of type 2 prudent self-avoiding walks was more than the number of prudent self-avoiding walks, which of course made me think that my program was wrong. And after a lot of messing around, I decided that my program was right and her results were wrong. And we wrote to her and said, we have this problem. And she wrote back and after had a look at it and said, yes, this is what I did.
She figured out what
Yep,
was
yep,
wrong.
but couldn't fix it. It's very subtle, because in fact I think the first 10 terms are correct of the series of her incorrect solution. It only goes wrong at the 11th term of the expansion.
So you later did numerical calculations for type 2 directly.
Mm-hmm.
You got a lot of terms.
Yep. I couldn't see immediately how to fix it, so we decided to proceed numerically.
So there's no known solution.
Wait. Be patient, Alan. I know it's orthogonal to your makeup. Anyway, we generated a very long series, in fact several hundred terms, and we found that the identical dominant critical behavior, that is exactly the same critical point with the same singularity, a simple pole.
Same as in type 1, you mean?
Yes. And a second singularity, also a simple pole, was found not far away, closer than the root 2 minus 1 singularity that we found for type 1. This was actually contrary to my intuitive expectation based on Keston's pattern theorem, because of course there are, in type 1, there are, in type 2 rather, there are patterns that can't exist in type 1, so by a naive application of Keston's pattern theorem, you might expect type 1 to be exponentially rare among type 2, but deeper reflection and discussion with Neil Madras made me realise that Keston's pattern theorem doesn't apply to this, and so it's not a. My intuition may be right, but I was using the wrong theorem. We searched for an ODE, failed to find one, and subsequently, and this will be presented at FPSAC 2008 in a paper that will appear any day now on the archive, Mireille Bousquet-Melou has found the solution for type 2 prudent self-avoiding walks. It needs 2 catalytic variables, that is, she has to keep track of the distance of the endpoint from 2 places on the boundary, and it's it's an admirable calculation, but a very difficult calculation, and the results are horrible. They are quotients of Q functions with arguments which are complicated algebraic expressions. So it really is ugly. But the structure is nice. You can see the structure. There are various zero. In fact, there are a bunch of. This is the first 0 of the denominator, giving you the critical behavior. This is the second 0 of the denominator, and in fact, there are zeros of the denominator that become dense in the interval as this approaches root 2 minus 1. You have an infinite number of poles.
You didn't define catalytic.
It's a technical expression used when you use the kernel method. It's the number of unnecessary variables that you carry around in the calculation that you then set to 1 at the end. But you need them to keep track of all the geometry.
Wait for the next call.
Beg your pardon?
Wait for the next call.
Yeah. Okay.
From chemistry, catalytic. You put a catalyzer, then you release it.
So there is still no, in anticipation of your next question, Alan, we still don't have a complete solution for the full problem. Ducci studied this problem, again by considering subclasses which are less numerous than in the case of type 2 because of the symmetry. And these, of course, can finish on any of the 4 sides of the minimum bounding rectangle. And this is, I didn't show you this. This is a typical type 2. Again, it's a sort of sequence of directed walks which can be directed either eastwards, northwards, or south. And you get something that looks like this. And for for the full ones, you get this sequence of directed walks that can go in sort of any direction as long as you don't violate the prudent condition, which I started to do when I sketched it. So ignore this little bit and that little bit. The general shape, as I say, is a sort of a spiral followed by a sequence of directed walks oriented in any way parallel to a lattice axis. Ducci obtained a nice result for this, 2 coupled equations which can be alternately iterated, giving a polynomial time algorithm for the generation of the series coefficients, and Andrew Rechnitzer has shown that these can be combined into a single equation, which in fact contains 3 catalytic variables, u, v and w. T is the expansion parameter, and you iterate this equation to generate the series expansion, and then set u, v, w equal to 1 when you've done that. So this is the infamous John Dethridge. obtain 400 terms in the series, first by going from this equation, secondly by direct enumeration, because at this stage we didn't know what was correct and what wasn't, and when we got agreement we believed this equation. And again we find that we have exactly the same critical behaviour for prudent self-avoiding walks as for type 1 and type 2. Same singularity position, same exponent, a simple pole at 2.48119. And a string of singularities a little further along the real axis appearing to accumulate at root 2 minus 1 as for type 2.
But not at the same places as in type 2?
No. To try and get some feel for the solution, it's useful, and this is going to be in fact the subject of a seminar David Wagner has asked me to give next Friday. How do we try and get some feel for the analytic structure of unsolved models? We very briefly, we anisotropize the model. That is, we distinguish between steps in the x and the y direction. And if we let Cmn denote the number of prudent self-avoiding walks with m horizontal and n vertical steps, then we have a two-variable generating function where Cmn is as defined, x is conjugate to the horizontal steps, y is conjugate to the vertical steps. We can express this as a single sum of these hn's, where now the hn is the generating function for prudent self-avoiding walks with precisely n vertical steps. So that h0, of course, is just a straight line. h1 is something with just exactly one kink in it, etc. And it's not difficult to prove that these generating functions are rational. And if we write them as a way this observation would suggest, as a rational function, it's also, well, slightly more difficult, but it's possible to prove that the denominators have an extraordinarily simple structure. That is to say, they are products of cyclotomic polynomials. And one of the things I'll be talking about next week is the significance of this. If you look at the structure of this denominator, it kind of gives you a clue as to whether your problem is going to be solvable or not. And if you look at the denominators in this case, these are the cyclotomic polynomials, psi1, which is 1 minus x. And so for h1 you get psi1, then you get psi1 squared, psi1 cubed, and psi2 appears. Then psi2, then we get psi3, then psi4, psi5. And this is now an empirical observation, is that these lattice statistical problems in which you get a steady build-up of cyclotomic polynomials of increasing degree as you increase the n in that generating function, is indicative of a problem that is very difficult to solve. And I haven't got time now to make that more precise. Well, one thing I can say, if you get this build-up of zeros, it immediately follows that the solution cannot be differentially finite, because you can't have an accumulation, because what this is telling you is that you've got an accumulation of zeros on the unit circle, and you can't have a differentially finite function, which is a function which is representable as an ordinary differential equation with polynomial coefficients. They can't possess this property. So this is a ad hoc test that I found extremely useful to apply. When you find this, you know you've got a tough problem. You see exactly the same behavior for example, for the self-avoiding walk generating function, which you can also anisotropize. If you look at the Ising model in 2 dimensions, you can do exactly the same. For the Ising model in 2 dimensions, you find for the spontaneous magnetization and for the specific heat, for which we know there are solutions, the cyclotomic polynomials that appear are only psi1 and psi2. As soon as you go to the susceptibility, you get this this build-up of zeros. So it's telling you that the fact that you only get psi1 and psi2 is suggesting this isn't a statement this isn't a theorem, because there are exceptions to it, but loosely speaking, as soon as you only have one or two cyclotomic polynomials in the denominator, you can be optimistic and hope that your solution will be D-finite, and then you can do experimental mathematical techniques, generate the series expansion and search for D-finite solutions. And in the case of the Onsager solution or the spontaneous magnetization of the Ising model, you'll find it quite easily.
Tony, what do you get for type 2 prudent walks?
Psi1 and psi2 only. So it tells you that it's worth trying to solve it. But it doesn't mean it's D-finite. In fact, it isn't. But it's solvable. So it's I might just digress for a moment to suggest why I think this is such a useful observation, inspired by a discussion I had with John Hammersley some years ago, who made the remark that it is much easier to prove something when you know it is true. And he gave us an example that I don't remember the details of the problem. A problem he worked on, we all have these problems that you can't do, and you have a new idea and you try it and it doesn't work and you put it away, and then a year or two later you get another idea and you try it and you put it away. So he had one such problem which he couldn't solve. And don't quote me on this, I'm quoting John Hammersley. He said that he was working on this, he put it away, and then he heard that Eddie Cohen had solved it. And he thought, I'm smarter than Eddie Cohen. If Eddie Cohen can solve it, I can solve it. So he pulled it out and he redoubled his efforts and had some other idea and solved it. And then he subsequently met Eddie Cohen and said, how did you solve that problem, by the way? Because I did it this way. Eddie Cohen said, I haven't solved that problem. So all you have to do is believe something is true and you might be able to solve it. Anyway, moving on. I want to turn now to the polygon analogue of prudent self-avoiding walks, which we call prudent self-avoiding polygons, not unreasonably. We define these as prudent self-avoiding walks.
May I ask a question?
Sure.
Is nu still 1?
Yes.
Yeah.
Unfortunately, we can't get away from that. We define these as prudent self-avoiding walks which end adjacent to their starting point. We can similarly define type 1, type 2 and full prudent self-avoiding walks. So here's a typical example of a prudent self-avoiding polygon with the end point adjacent to its starting point, and then you can make a polygon by adding a bond. The type 1 restriction means that these polygons just look like bar graphs with a long tail that closes. So they're pretty uninteresting looking things. They look something like this. And then the tail has to come around there to close near the origin.
If you forget about this closing, do they look like the opening?
If you forget about the close, well,
if
it
you
depends.
Forget about the long paths, straight paths you just had, do they look like the formula?
They're bar graphs in that sense, yes. But you lose a lot, as you will see. By this is a very severe restriction. We've only found the solution at this stage experimentally. It should be easy to prove, but I haven't done so yet. These are quite recent results. It should be fairly easy to prove. And if we denote the number of n-step type 1 polygons by Pn1 with generating function P1x, we find this to be the generating function. So again, let me emphasize, this is a result of experimental mathematics. We generate the coefficients. I've got some little search programs that I run, and out pops the answer. And you can see that you only need something like 9 or 10 values of P1 to find the solution. And if we have 500 and they're all correct, it's a not unreasonable conjecture that this is indeed the solution, and it shouldn't be too hard to prove it, as I say. The solution also satisfies a second order Fuchsian ordinary differential equation of no particular appeal. But notice that the singularity structure, you've got a simple pole here and you've got a square root singularity here, which has a 0 closer to the origin than 1. and this is a different polynomial to that which occurred. Replace lamp. I hope that's not urgent. From this it can be seen that these behave like tau 1 to the n to the minus 3 halves, where 1 over tau 1 is the smallest positive root of the polynomial that appeared, and that's there, which is equal to this. So it's this number that should be compared to mu. So unlike self-avoiding walks, for which we have Hammersley's result that mu for polygons is the same as mu for self-avoiding walks, this result at the bottom here, this is not the case for prudent polygons of type 1. The growth constant is there. These are exponentially rare among prudent self-avoiding walks. And the reason for this is that the fact that the general shape of one of these guys, as you can see, with mu equals 1, is such as to really force the endpoint away from the origin. So the fact that the endpoint has to be next to the origin is quite a tight restriction, and it's that feature that, in a hand-waving manner, means that they're exponentially rare among prudent walks. As I say, so that we can compare that result 2.48 to 1.84. And of course, if you try and apply the same method of proof as used by Hammersley, an unfolding method to show that mu for walks is the same as mu for polygons, you can see exactly where it breaks down. So prudent polygons are exponentially rare among prudent walks, unlike the situation for ordinary self-avoiding walks. So if we turn now to type 2, these look like, well, like these guys, again with a long tail that has to come back here. So the fact that they can go off in various directions means that it's probably not quite as hard to come back and close at the origin, but heuristically you may expect also that mu will be still smaller than the corresponding result. To cut a long story short, we generated some quite long series. We didn't find a solution, but series analysis tells us that the asymptotic behavior of the coefficients is the same in the fact that the critical exponent is the same. We've got an n to the minus 3 halves. We've got a different growth constant. It grows as 2.02 to the n instead of 1.8 ... but that's again smaller than the corresponding result for the walks. Again, this anisotropy test shows a simple structure which suggests that the problem should be solvable. That should be just like for prudent type 2 walks, and it would be interesting, which again is something I haven't done, to apply the techniques that Mireille Bousquet-Melou used for prudent type 2 walks to prudent type 2 polygons to see if we can solve those as well. The nature of the anisotropic generating functions is like this, which answers the question Thomas asked about prudent walks. So that these Hn functions have cyclotomic polynomials, just psi 1 and psi 2, 1 minus x and 1 plus x, and they occur with powers n over 2 for n even and power n for n odd. And the numerator polynomials are of degree n or of degree 2n, respectively. Finally, for the full prudent self-avoiding polygon series, we have some 150 terms. Our results are unfortunately inconclusive. This is one of the most difficult series I've ever had the misfortune to try and analyze. We find that they grow like tau to the n to the theta, where 1 over tau is 0.226, so that's 2.1. So again, they are exponentially more numerous than type 2, exponentially rare among prudent self-avoiding walks. The exponent is surprisingly difficult to estimate. For type 1 and type 2, we had n to the minus 3 halves. We had theta was 3 halves. Here our best guess is theta is around 4 or 4.5, which is quite different from the exponent characterizing type 1 or type 2. And perhaps the most, I mean, using Allen's test, I wouldn't even bet a euro on this, though I would bet a euro or even 10 that theta is different to the case of type 1 or type 2. But it is an extraordinarily difficult series to analyze, I suspect because we've got a large number of zeros on the real axis very close to this singularity, which is making it so difficult. Note that the 3 critical points for type 1, type 2, full polygons satisfy this sequence of inequalities. So unlike the hierarchy of prudent self-avoiding walks, prudent self-avoiding polygons have growth constants that vary with model, indicating that type 1 are exponentially rare among type 2, which in turn are exponentially rare among full prudent self-avoiding polygons. In 3 dimensions, we generated some series for 3-dimensional prudent self-avoiding walks defined naturally. That is to say, the endpoint can't see the origin by continuing along a lattice axis. Such walks must also lie on the perimeter of their minimum bounding box, and these are the results we find. It grows like kappa to the n to the gamma minus 1, where kappa is 4.494 and gamma is around 1.66. Again, these are error bounds that I wouldn't bet my house on. I might bet your house on them. But for comparison, for 3D self-avoiding walks, we have mu is around 4.68 compared to 4.49. So you can see these again exponentially rare. Gamma is different, but gamma is more interesting than in the 2-dimensional case. It's certainly not a pole or a double pole there. Though for the mean square end-to-end distance in 3 dimensions, we find nu is about 0.63. Certainly not a half, certainly not 1. By comparison, for 3-dimensional self-avoiding walks, nu is around 0.587. So not surprisingly, prudent walks are a bit more spread out. The prudent condition means that you're forcing the endpoints further apart, which is reflected in this slightly larger exponent.
Not much.
Not much.
Because now it can go towards the rest of the walk by seeing a hole in it.
Yep, that's right. Yep.
It's a big deal.
Yep. Yeah, so it's not nearly as strong a constraint.
Yeah.
And of course, in 4 dimensions.
Do you think that a dimension above 4 prudent self-avoiding walks might just be in the university class or in the salary class of ordinary random walks?
Yep, I think so. So in conclusion of this section, and in fact I suppose looking at the time in conclusion for this talk, we've investigated 6 models in 2 dimensions, type 1, 2 and full prudent self-avoiding walks and polygons, and prudent self-avoiding walks in 3 dimensions. Ducci gave a solution to type 1 prudent self-avoiding walks and a polynomial time algorithm for producing the full beasts. Bousquet-Melou has now given a solution to type 2. We have exponential time algorithms for all models. We have an unproved solution for type 1 prudent self-avoiding polygons. I believe type 2 prudent self-avoiding polygons are also likely to be solvable following Bousquet-Melou's solution. Prudent self-avoiding walks and prudent self-avoiding polygons almost certainly are not D-finite. I mean, this is something I am prepared to bet $1,000 on. Prudent self-avoiding walks in 3D seem to be the closest model to true self-avoiding walks that we have, though of course the model is extremely unlikely to be solvable. And just to mention what will come up in Vienna, quasi-prudent walks. So Jim Prof suggested weakening the prudent condition by this. Mireille gave a seminar on this model in America, and Jim Prof was in the audience and suggested this, that why don't we weaken the prudent condition by allow walks to step in the direction of a previously visited vertex, provided they can see infinity. That is to say, they can escape. Let me try and make that a bit clearer.
They can see infinity along some lattice axis.
Along a array, yeah.
Oh, a lattice.
Along a lattice axis, exactly. So you can't go like that if you're prudent, but you can go like that if you're quasi-prudent, because you can see infinity out here along a line at right angles.
So you can see infinity from the endpoint,
Yes.
not from the
Always
starting
from the
point,
endpoint.
last.
We're always talking about what you can see from the endpoint.
No, sorry, the difference was between you are adding an edge ij.
Yes?
You can see infinity from j, not from I.
Correct.
And so now from here you could not go to the left anymore. Because
Correct.
the self-avoiding walk could.
Yes. In fact, the self-avoiding walk can trap and be of finite length.
Yeah.
Yeah. So I'll just show. Cool. So at this stage, if you're prudent, you can't make a right hand, but so here you can. You can go up, and then you have to go to the right. Well, given the time, I will stop here and tell you about quasi-prudent walks in Vienna or at morning tea.
Thank you very much. We have had lots of questions already, but I'm sure there are more.
Just a simple question. Can one be prudent on other lattices?
Yes, Mireille Bousquet-Melou has, in fact, also discussed prudent walks on the triangular lattice, where in fact it turns out that simplifications can be made, and she has been able to solve the complete problem on the triangular lattice.
Does she get the same exponent?
Yes.
Vincent?
Do you expect, is this scaling, would you expect it to be a conformal invariant theory at the critical point, or?
We pull the same face. I don't know. I doubt it. I think this is some sort of this is really a. It's a. Well, I'm happy to be interrupted, but my feeling is no. But what do you think? Yeah.
I had the same feeling.
Yeah. Xavier.
Yes, you mentioned this formal power series, which is seems to be horrible for you. Q series, where you substitute Q as an algebraic generating function.
Yes.
And there is another nice example of by Bousquet-Melou in Rechnisser.
Yes, bar graph polygons.
By
Yes.
multi-directed animal,
Mhm.
where you have also a Q series,
Yeah.
not too complicated, and then you substitute the Q by the generating function of Catalan number.
Mhm.
So I think some new series are appearing, a new
Yes.
class of power series are appearing,
Yep.
which are above the definite class.
D'accord.
So there should be, general, maybe some study or two. Do you think it's?
Yes.
That,
I've been thinking along very similar lines.
And even some of them have Bajic hypotheses. So I have hopes that more general things can be done and so on.
Yeah.
How much money are you ready to invest in this program?
I prefer to use government funds to invest in this program. I think.
Other questions? May I then give my own brief summary of this talk and a piece of advice? You should try to find somebody who is less smart than you are, which in some cases is difficult, and then follow his work very closely. Thank you.